Hello everyone, and welcome to the 22nd Surface Ventures webinar. Before we go any further, I just want to check that everyone can hear me okay, and just sort of see where you're all joining from in the chat. I see some people have typed already in there, but it'd be great if you could say hi and where you are in the world right now. Okay. Oh, excellent stuff. India, UK, Kuala Lumpur. Fantastic. Great to see. Great to see. Okay, so my name is Sam McMaster, and I am the event manager at Surface Ventures, and I will be your host today. Here at Surface Ventures, we're a non-for-profit organization, and our mission is to provide world-class surface engineering education for academia and industry. Every month, we bring you a sector-leading speaker to present the current challenges and future trends in surface engineering, alongside surface engineering workshops and live equipment demonstrations. So, great, good to see you all. Good to see you all typing in the chat there. So, apologies for the slight difference in the slides there. Unfortunately, our VP Tawheed Khan was unable to make it today, and hence I am hosting. But for now, I would like to introduce Professor Su8 Kumar Sinha from the Indian Institute of Technology in Delhi, India. And I will invite Su8 to the stage right now. Professor Sinha is a full professor in the Department of Mechanical Engineering in the Indian Institute of Technology in Delhi. Prior to this, he also worked as faculty in the Department of Mechanical Engineering, the National University of Singapore, and briefly at the Indian Institute of Technology in Kanpur, India. He holds a PhD degree from Imperial College London and a master's degree from the Indian Institute of Science in Bangalore. His major area of research is in the field of tribology, and he is presently focusing on finding improved polymeric materials for the acetabular cup used in hip implants for total joint replacement. In terms of agenda, we'll start with our speaker's presentation, and we will show some videos from Optimal Instruments, our sponsor for this event, before we move finally on to the Q&A. Quick note about questions. Please do type these in the chat, and I will mark them for the Q&A session. We're aiming to go for about 60 minutes in total today. Additionally, there will be poll questions and handouts released. So these handouts will be of interest to you who are interested in Optimal Instruments equipment, and poll questions to find out a little more about you. If you answer these, someone from Optimal may get in touch to provide further support. We will also be offering attendance certificates for all of the attendees who are here live today. I will share the link to generate that certificate for you later in the event. And a quick reminder about our website, surfaceventures.org. So on that, you will find the videos from our previous talks, information regarding upcoming webinars, and information about the Surface Ventures team. So let's start with a quick poll question. That is, what is your current role? And making that live now. Okay. Su8, could I ask you to come on stage, please? Wonderful. Yeah, thank you very much. So great to see everyone. We've got some researchers, students, and some industry members there. That's always great to see. Welcome to the stage, Su8. It's great to have you.
Thank you.
So with that, I will take the intro slide off. Please go ahead and set up the screen share, and I'll hand it over to you.
Okay, thanks, Sam, and thanks to all the people present here today to listen to this talk. So I'm quite excited to give this talk. So let me just share the screen first. Yeah, can you see my screen now?
Not quite yet.
Okay.
There we go. It's up.
Okay, so
Excellent. So good. Oh, great. I was just about to ask you to hide that little pop-up.
yeah.
So I'll leave stage now and hand over to you. Great stuff.
Okay, thank you very much, Sam. So hello everyone. So this talk I have prepared is on tribology, and more specifically on bio-tribology. As some of you might be already aware of this topic, tribology and bio-tribology. So in bio-tribology, basically what we do is we study materials which can be man-made materials, or it could be biological materials, for application in our body system, for applications where there is going to be some friction and wear issues involved. And the important ones are the knee joints, the hip joint, and these kind of applications where the materials may wear out and the friction may be very high. So these are the application areas, and basically what we need is implants. So when our the original body joints get damaged because of disease or because of any reason, then it has to be replaced. In many cases, it has to be replaced by implants. So these are the implant materials that we design and we make for this application. So in bio-tribology, one polymer which is known as ultra high molecular weight polyethylene, UHMWPE, is used quite often for hip joints, hip implant, for knee implant, and so on. However, the performance of UHMWPE has not been very good in terms of the life of the implant, because wear does take place. We should know that UHMWPE is a very, very efficient tribological material, tribological polymer, and therefore it is quite hard at the present to replace UHMWPE. However, efforts has been on to find a replacement or improvement of UHMWPE so that we can increase the life of the implants. So in this talk, basically I will talk about some of the non-UHMWPE polymers and composites that has been tried, and also we also have tried in our research. So before I start, I would like to acknowledge these individuals. Many of them are students and some of them are my collaborators, like Professor Su8, who is quite well known in this field. And also we have been supported by JSPS and DST grant for this kind of work. So osteoarthritis is a kind of problem in our joints, or disease, is a extremely debilitating health problem. It can happen because of the aging, or it can also happen because of injury or any kind of other disorder. And this problem is very serious for hip and knee joints because our most of day-to-day activities require use of these joints. The body weight is completely borne by these joints. So you can imagine that we just cannot function without our joints working nicely, the hip and the knee joints. So these are extremely important, and therefore any issue related to these joints, such as pain or arthritis, then it will be a big problem for us, for our quality of life. So as you can see here, these joints, especially I will be focusing more on the hip joint, these joints have been replaced by implants. So here in this case, for example, the acetabular cup is attached to the pelvic side of the bone, and the femoral head is attached to the femur of the our thigh bone, and they will articulate with each other, and in between these two there is a liner, which is a plastic liner, and this is the UHMWPE. So this liner gets fixed to the acetabular cup, and basically the sliding that happens during our movement is between the femoral head and this plastic liner, which is UHMWPE. So during this interaction, it is mainly sliding, and it is called cross shear sliding. That means the sliding is not linear. It crosses the track, and because of this crisscross sliding, the wear is extremely high. Wear is quite high compared to a linear kind of sliding. This joint is also helped by the synovial fluid, which our body secretes in this area. So this fluid acts as a lubricant. So overall, this joint or this artificial joint or implant can work quite effectively. But some of the materials get worn out, like plastic, the UHMWPE part, where debris comes out, and also this part, which is made of metal or ceramic, and especially the metal part will wear out, and these metal ions will enter our body system. Similarly, the plastic side, the wear debris will also go into the tissues, and there it will cause problem for the body, because the body may think these debris as foreign elements. So this is how the body reacts to these wear debris. So our main goal here is to find a replacement, or at least improve UHMWPE such that we can reduce the wear debris formation for the metal part, for the polymer part. The metal part also has got the issue, but right now we are not focusing on the metal part. We are focusing on the polymeric part. Several solutions have been proposed, but at the moment total hip joint replacement is a kind of most practical solution. If you look at our joints, it is a hierarchical structure of cartilage. So basically the bone is covered with a cartilage, and cartilage is extremely smooth and very lubricating surface. And if you go into the structure, you will find that this cartilage has got the deep zone, the middle zone, and the superficial zone. So superficial zone is the one which is actually interacting with its counter surface. So counter surface is also another cartilage. So basically two cartilages are interacting with each other. But on the top surface, we have got many things. And for example, here it shows us the top surface, and the top surface has got proteoglycan, which are macromolecules, as well as phospholipids. So this whole part of this cartilage is called extracellular matrix. So basically, extracellular matrix provides the necessary structural strength, and most important is the frictionless or nearly frictionless situation here. So in a healthy joint, as you can feel that the joints are very frictionless. Friction is extremely low. So this is the characteristic of the lubrication system. Many lubrication theories have been proposed. So it is believed that this lubrication is basically a mixed lubrication. That means the liquid films are formed partially, and also this cartilage, this part of the top cartilage, acts like a spongy material. That means it keeps lots of water and the proteoglycans, all the lubricating molecules, and whenever under stress, these water and the proteoglycans are released, and they provide the lubrication. This is also known as boosted lubrication. So many theories have been proposed, and So this is the original, the cartilage. And if you look at the much more in detail on the cartilage, it has got these fibers, and further on these are the molecules, how the cartilage structure looks like. So this is part of some simulation which we have been carrying out to understand how cartilage slide against each other and how friction is generated, as well as how wear is generated. So this is some sort of brief on understanding about the cartilage and the lubrication system. If you talk about proteoglycans, it has got many macromolecules, hyaluronic acid, lubricin, aggregants, and also the phospholipids. So this is a schematic of the joint. So these are the two parts of the bones and the cartilage coverage here, and this is filled with the synovial fluid. And the synovial fluid contains these molecules. So these molecules are basically scattered on the cartilage surface, on the top cartilage surface, which forms the superficial layer on the top, which is basically interacting with each other. So this gives a structure of the cartilage, starting with the bone structure, subchondral bone, and how the cartilage changes, and the top layer is the superficial layer. So this is a good for us to understand about how our natural system works, so that in the implant, for the artificial system, we can try to mimic some of these activities that happens in the nature. So much more in detail about these the top layer molecules. So you can see that the collagen network is in the cartilage, and lubricin molecules, hyaluronic acid molecules, as well as phospholipids, they are here. So these together provide the lubrication for our system. And some of these molecules, especially these phospholipids and lubricin, they are charged. Overall they are neutral, but they have localized charges, the positive charge and the negative charge. And these localized charges basically attract water molecules, because water molecules are dipole systems. So therefore they attract water molecules and they hold water molecules for lubrication purpose. So this is the way how nature works for water lubrication. So hopefully our goal is in the future we will be able to mimic all the functions and provide an implant which is as good as, or at least very close to, the natural system. Another thing to note about this is that the proteoglycan aggregates or proteoglycan molecules have got the central link protein and some the core is the protein, and these molecules are attached or arranged in this fashion so that they can work for water lubrication, and the positive and the negative side of it, they will attract water molecules and they will hold the water molecules. So this is a explanation of the natural system. Now here is more detail about how the implant is made. So this is the acetabular cup made of metal. This is on the pelvic side of the bone, and this is on the thigh bone or femur, and this is femoral head. So the sliding will take place between UHMWPE liner, which is attached to the acetabular cup, and the head part, which is made of metal, cobalt, chrome, molybdenum metal, or it can also be made of ceramic. So UHMWPE has been the polymer part of hip and knee prosthetic joints since 1960s. So if you go into the history of this, actually this is a very, very successful polymer, and this started with Charnley, who introduced this polymer, and this polymer worked very well. But later it was further improved by cross-linking. So cross-linked UHMWPE showed improved mechanical properties. However, wear and fatigue properties deteriorated because of oxidative degradation. So because cross-linking in UHMWPE using gamma irradiation produced many radicals, and that led to oxidation of UHMWPE. So later vitamin E was included, and this solved the problem of the oxidation because it acted as antioxidant, and wear and fatigue problems were reduced because of which happened because of oxidation. So vitamin E has been used for cross-linked UHMWPE to improve its wear and as well as fatigue problem. Here you can see one of the knee implant here, and the wear takes place by what is known as adhesive wear. That means the metal actually sticks to the polymer part, and gradually it removes the polymer part because of the fatigue action. Oxidative wear and the fatigue wear also takes place in this part. Oxidative wear because you can see some discoloration and some changes in the molecule size. This UHMWPE is a very large molecule, but because of the mechanical shear and some chemical oxidation, the molecules will basically break down. So these are all part of the failure mechanism that takes place in UHMWPE. The wear particles are not good for our body because these wear particles are taken by the macrophages. So macrophages are in our body basically to consume any kind of foreign elements, which if the body identifies them as foreign elements, it could be bacteria or virus, but it could also be these wear debris, which are micron to submicron in dimensions. So people have found that in tissues, UHMWPE particles are taken by these giant cells, and the body will react to this action. That means some inflammation, some swelling will happen on the joints or near the joints, and this can eventually damage the implant itself. So which means then the implant has to be actually reinstalled. That means revision surgery, and revision surgery is not a desirable option for any patient. So our goal is to make sure that the debris particles that come out of UHMWPE, first of all, there should be as little as possible, and if they come out of the implant, then they are not considered by body as harmful. So let us try to understand these materials that we are working with. Basically, these are within our control, the materials that we use, UHMWPE and some other materials. So if you work with UHMWPE, you will understand how the coefficient of friction will show. So in general, in a dry interaction, so that means if UHMWPE is dry sliding against a metal surface, you will get quite high coefficient of friction. But if there is a lubrication of bovine serum liquid lubrication, then the coefficient of friction will come down, and this shows that it responds to the lubrication. In general, the specific wear rate we will see is in this range, which is 3.93 multiplied by 10 to the power minus 7 millimeter cube per Newton meter. So this is the unit of specific wear rate, mm cube per Newton meter. So always we will compare this number whenever we are trying to replace or we are trying to improve UHMWPE. At least it should, the wear rate should go down. Only then we can say that yes, we have improved the material. So what other material options we have? We can make composites of UHMWPE. That means we can add particles or fibers to UHMWPE. Other material that has been tried is PEEK, or polyether ketone, and its composites. Hydrogels are another group of materials which are very useful, and the most famous hydrogel is PVA, or polyvinyl alcohol. Then polymer brush grown on hydrogels. So different kinds of polymer brush have been prepared, and they basically mimic the proteoglycan behavior, which also acts like a brush. And if we have these brushes on top of hydrogels, then perhaps this can mimic our cartilage to some extent. Another combination of material that we have been working on is the epoxy and UHMWPE composite. So I will show you data on these kind of alternatives to UHMWPE, as well as on the fifth one, which is our research topic. So for example, if you look at the literature on UHMWPE composites, so here for example, Multiwall CNT, and in this work, as MWCNT has been added to the UHMWPE, wear rate has gone down, and friction coefficient has also gone down in dry condition as well as in lubricated condition. So this is for dry condition, and this gray one is for lubricated, where they used distilled water as a lubricant. Here I should say that what kind of lubricant we can use. So many times researchers use distilled water, but also people use bovine serum, which is more closer to our actual synovial fluid. So the wear and friction behavior will depend upon what kind of material we use as a lubricant. Dry, of course, dry property will be quite different. So here we generally start with testing with dry in the dry condition, and later we move on to the lubricated condition, which is closer to the actual joint. So here we see that adding CNT, Multiwall CNT, has reduced both friction and wear, at least in this research. And it was found that wear mechanism for pure UHMWPE was plastic deformation, and for the composites it failed by delamination and significant cracking. So here we can understand that because of adding a filler like CNT, basically the material became a little bit brittle and cracking initiated. Pure UHMWPE is very plastic material. It deforms in a plastic manner, very ductile material. But if you add a filler, whether a particle or a fiber, it changes its behavior from very ductile to somewhat brittle. And wear, especially wear, takes place by delamination, cracking, and removal of the fibers or the fillers. Some of our works have also been represented here. So for example, these specimens we have prepared pure UHMWPE, then UHMWPE with PFP coating, which is perfluoropolyether. Then we have used 12% nacre UHMWPE and some percentages of CNT. So these tests were conducted on a pin on disc apparatus. So that means these specimens acted as the pin, and we had the disc of stainless steel, and we were sliding in bovine serum as the lubricant. So first of all, when we conduct this kind of tribological research, we start with finding out the mechanical property, that means the bulk mechanical property, and we find out the hardness. So hardness will change if you add some fillers. Okay. However, in this case we have seen that the change is very minimum, not almost not much except in this case. So more or less the material remains same in terms of its bulk property. And when we conducted the sliding test, so this is a pin on disc test with bovine albumin protein solution as the lubricant, and we found that all of the composites we made of UHMWPE actually gave wear rate which was slightly higher. So even the CNT, which you saw in the previous paper, that Multiwall CNT gives wear rate which is lower than the wear rate of pure UHMWPE. However, in our case we did not find. We found that the wear rate is either nearly same or slightly more. So this one was little bit of disappointing because normal expectation is that when we add some strong fillers to a polymer, the wear rate goes down. This shows the SEM picture of the same polymer composites that I have shown you before, and you can see that UHMWPE, even after adding some filler, it acts in a very ductile manner. We don't see any crack. All we see is deformation of the material in a very ductile manner. So in our work we concluded that particle reinforcement or liquid lubricant such as PFP added to UHMWPE has not improved wear resistance, or the improvement was very minimal. Other types of composites people have formed is adding carbon fiber to UHMWPE. So as we know that adding any kind of strong fibers like carbon fiber or Kevlar fiber or glass fiber will improve the bulk property, and in many cases it will improve also the tribological properties. So here we have got carbon fiber addition to pure UHMWPE. So this is for the dry sliding. Again, the apparatus was block on ring with the liquid or in the dry condition. So for dry condition, composite gave slightly higher coefficient of friction, but for the lubricated case, these two are for the lubricated case, pure UHMWPE, and this is the composite of carbon fiber. And you can see that there is a drastic reduction in the coefficient of friction. So here we see that having carbon fiber in the matrix of UHMWPE has helped in the lubricated case. Again, the experiments were done in a distilled water lubrication, so we need to also check how the results will show if we use bovine serum as the lubricant. And even in the wear rate, we found that with lubrication the wear rate actually goes down. So this is a carbon fiber percentage, weight percentage. So 5%, 10%, 15%, 20% and 30% of carbon fiber. So as we increase the carbon fiber weight percentage, the wear volume goes down compared to the pure UHMWPE. So this is quite encouraging result, especially for the lubrication one. But as I said, this was done in distilled water, so we need to evaluate it in bovine serum and see whether we can get the same result. Again, I should tell you that in the bio-tribology we may start with pin on disc test, but we have to move on to a cross shear type of test. And one test which is done is called multidirectional pin on disc, or MDPOD. And beyond that we should use a simulator. So again, all these tests are done in vitro. So we need to evaluate the performance of the material in simulator before any further in vivo trial can be done. So it's a long process. Here you can see that ACM micrographs of one surface, 20 weight percentage carbon fiber, reinforced UHMWPE in water lubrication. Just the previous data I have shown you. But here what we can see that, of course, UHMWPE will deform by plastic deformation, but here we do see some fiber pull out. And this kind of fiber pullout may not be very good for implants, because these fibers will again act as a wear debris, or it will the body will react to the presence of these carbon fiber. So this is another issue, and in fact UHMWPE and carbon fiber composite has been tried clinically. So this is a paper where failure of carbon fiber reinforced polyethylene was studied. So that means in some patient it did fail, and so those failed specimens were looked at, and what they found is that these fibers actually on the surface where the sliding takes place, the fibers actually gets pulled out, because these fibers are in the horizontal condition like here on the surface, and they get easily pulled out because of the shear stress. So this is one big issue, and in fact because of this reason this composite was tried quite early on in 1988, but since then this composite has not been tried so much. And what the authors of this paper found, that the failure was related to the poor bonding between the fiber and the matrix. Matrix is UHMWPE and the fiber is carbon fiber. So it was more of the manufacturing issue rather than the material issue. So perhaps this type of system can be again tried, and in this one the manufacturing part has to be resolved. That means the bonding between the fiber and the matrix has to be good. So here fatigue failure due to poor bonding between the carbon fiber and the polyethylene particles, and poor fusion of polyethylene particles during compression molding was mentioned as the possible case of failure. So however, these kind of composites have not been tried since then, basically fearing about the issues that happened for these patients. Other type of combination, we have PEEK and its composites. So some researchers have, as you can see here in this paper, some researchers have started working on PEEK, polyether ketone, as a replacement for UHMWPE. PEEK is a very good engineering material. It has got better mechanical strength compared to UHMWPE, almost double, and it has better creep resistance as well. But tribologically, PEEK is not a very good material compared to UHMWPE. It gives slightly higher friction, and wear is also high in the dry case. But here the authors have tried different composites. So one composite was with carbon fiber, another carbon fiber and graphene, and another one is with glass fiber, whereas this one is pure PEEK material. And here the new things they have tried is that they have slid the polymeric part against itself, another polymer. So the pin is the polymer and the disc is also the polymer. So here the sliding is not taking place between the polymer and the metal or ceramic, but rather polymer against polymer. And the idea is that this can give us even lighter system. So it will be lighter, and also it will reduce the problem, or rather eliminate the problem of metal ions that I was talking about. That metal ions get released from the metal part and it goes inside our body and causes some harm. So having both side as polymer or polymeric material would be an advantage. And so sliding against itself, so for example pure PEEK sliding against pure PEEK, and the composite sliding against composites. And here you can see that pure PEEK has got lowest wear, as well as the carbon composite. The composite with carbon has got lower, almost close, very close to each other, but glass fiber did not work very well. So here we can learn that carbon fiber in general has done quite well. Although the previous result I showed you where there were cases of failures for 2 patients, but the conclusion was that it was because of the poor bonding between the fiber and the matrix. So Perhaps carbon fiber has got some promise here. Glass fiber did not show very encouraging results. So this is the case of polymer sliding against polymer. It was not compared with the metal, how it compares with the metal, so we can only see the results of this polymeric material against polymeric material. And this shows the wear surface, which gets completely polished surface, and here you can see this is the glass fiber reinforced peak and where we get higher wear rate. So everything is within our expectation, and hopefully the polymeric material against polymeric material might be another choice. However, if we look at the failure of the polymeric composites, and here in this case the glass fiber one, and you can see lots of pull out of the fiber. So these fibers are longitudinally on the surface. So in the bulk they are random, but on the surface they are longitudinally arranged, and they get pulled out during the sliding that takes place. And as you know, this sliding is not full liquid film, but rather it is mixed. So there is always a possibility of dry interaction between the two surfaces. In this another work, PEEK was used, and PEEK was slid against UHMWPE. That means if we have got the acetabular cup of UHMWPE, then PEEK is the other part, or the femoral head. So here we have a comparison with the metal sliding against metal, cobalt, chrome, molybdenum. And here people have shown that when PEEK is sliding against cross-link UHMWPE here, it gives far better result. Okay, so the disc material is PEEK here, and the cobalt chrome is this one when the disc material is cobalt chrome, and this result is for the wear of the disc part. So as you can imagine, in a pin on disc machine test, both the pin and the disc wears out. So here we can see that disc wearing of the PEEK disc is much less compared to cobalt chrome molybdenum, and the pin part also, the pin of PEEK was wearing less compared to cobalt chrome molybdenum. So overall it is concluded here in this work that PEEK sliding against UHMWPE has better result than PEEK sliding against cobalt chrome molybdenum. However, I should say that this kind of results needs to be verified by third party, because in this work the work itself was supported by the company which made the PEEK. So there's it needs to be verified by independent research. Another material that we have is the hydrogel, polyvinyl alcohol, PVA as hydrogel. So PVA is being used, or this kind of hydrogels are being used for many other purposes within our body system, but for the joints, for hip or knee joints, this has not been clinically tested, but in vitro tests have shown good promise. So for example, quite early on in 1996, the PVA was used and some tribology tests were conducted, and it was found that PVA gives better result compared to UHMWPE when sliding against a glass surface in a simulated lubrication system. In one case water, another case glycerin 61 weight % with water solution. So PVA or hydrogel is being tested by many research groups presently. Further on, the same group have conducted PVA with PVA gel, and this is freeze thaw gel, and this is cast dried. So just different way of making these hydrogels, and it was found that PVA CD, which is cast drying process, gives a better result than the FT. And perhaps the hybrid one will give some better result. And these changes were because of the structural changes here. So for example, PVA freeze-thaw process gives these kind of microcrystallites which are aggregated at some places, whereas in the case of PVA CD gel, we have got these microcrystallites which is uniformly distributed throughout. And because of this, PVA CD is transparent, whereas PVA FT is not is opaque. So there is a difference in the crystalline structure, and overall PVA hybrid gel, that means it's a combination of FT and CD, gives a better result. So PVA hydrogel is another choice we have other than PEEK and UHMWPE composites. Not much work has been done on the wear aspect of hydrogel, but some results we have which shows that perhaps PVA FT or freeze-thaw process gives a better result, which has got less wear compared to PVA CD. So again, this part needs to be properly evaluated in vitro in our pin-on-disc machine or multi-directional pin-on-disc machine, so that we can understand how the PVA gel will perform in actual system. Friction wise, we have found that friction, it gives quite low coefficient of friction. Another solution people have research on is called Zitarian Polymers as boundary lubricant on the hydrogel. So these Zitarian polymer molecules are net neutral. So just like our proteoglycans, they are net neutral yet possess both positive and negative charges in close proximity to each other, often along a carbon chain backbone, and they have strong interaction with water molecules. So perhaps this kind of polymer molecules will mimic proteoglycan, and they will encourage water lubrication. So these Zitarian polymer can be included within the hydrogel at the surface of the hydrogel, so that they provide lubrication, whereas the bulk of the hydrogel will provide the mechanical strength to the implant. So perhaps future solutions will be a combination of this kind of hydrogel and Zitarian polymer or some other composite with Zitarian polymers. In this case, they have conducted the friction test, and they found that adding even 5% of Zitarian polymer will reduce the coefficient of friction to very, very low value, and it continues. So this is the friction mechanism is well established, but on the wear side, we do not have much data. I will show you now some results from our laboratory on epoxy and UHMWPE. So UHMWPE particles were used, and Su8, which is a kind of epoxy, was used as the bulk material. And I will not go much into the details of all this, but you can just compare the Su8 with conventional UHMWPE, that means pure UHMWPE. Su8 is a stronger material mechanically, but it has very poor tribological properties. But if we add these particles of UHMWPE into Su8, it gives a better result, far better result, so that we will see. So we have added Su8, and into it we have added UHMWPE particles, different weight percentage, and we have also added HA, hyaluronic acid, as another filler. HA acts as a lubricant in our natural synovial fluid. So this can become part of the composite material. So this is what we have done, and this is a curing agent because Su8 is an epoxy. It requires some hardening agent to start the hardening process. And the samples were made into the pin form, and then they were slid against a metal part, cobalt chrome metal surface, in a multi-directional pin-on-disc test. So I will show you some results on this with different percentage of HA, but UHMWPE percentage was fixed at 25% weight percentage, and they were also compared with pure UHMWPE. So this is a new wear test we developed. In this, what you do is one of the problem with
Sujit, sorry for apologies for interrupting. Can I? So we're coming up to about 10 minutes left of the of our sort of general hour of the event. Do you have many slides left?
a couple of, so how many minutes I have?
We say another 5, then we'll do the sponsor section and then
Okay, sure.
Q&A.
Sure, I will finish in
Thank
5
you.
minutes. Yeah. So in this, what we did was one of the problem with this kind of biotribological test is that these polymers will soak a lot of fluid, which is basically water and other proteins. And because of this, the wear evaluation becomes a very, very big problem. So here what we did was we made some holes on the pin surface, and as the pin is wearing out, the depth of the hole will be reducing. And this is how we will find out what is the overall wear. So we made some 5 holes at different places, and then we measured the depth of these holes to evaluate the wear. So this is the Vickers hardness test. So after adding these fillers in the dry case, you can see that there is an increase in the mechanical strength, but if we soak it in serum, bovine serum, then mechanical strength does not change much. That means because of soaking of water and these kind of proteins, actually the material becomes softer. It softens slightly. And most important, we have to see that coefficient of friction. So coefficient of friction actually is quite low. For UH25 means 25% of UHMWPE in Su8. Pure Su8 gives a very, very high coefficient of friction, but as soon as you add 25% of UHMWPE and then some percentage of HA, which is hyaluronic acid, and you get a very good surface, very low coefficient of friction. So HA02, that means weight percent 0.02, gives the very consistent low result, low coefficient of friction results. And it was slid for quite some time. The number of cycles were more than like 200,000. So this gives a very good system to work with. And in terms of wear, which is another important part, is that we found that this is also coefficient of friction. So average coefficient of friction in the steady state, and it gives a low coefficient of friction for our composites, even compared to the pure UHMWPE. So this is very, very encouraging. And we compare the wear rate, even though there are a lot of scatter in this kind of evaluation of wear rate, but our composite, which is 25 UHMWPE and 0.02 or 0.05 of HA, gives a low wear rate. So this is compared to pure UHMWPE, which gives 3.93 10 to the power minus 7, which is much higher compared to these. So overall, we have achieved a very good low friction and low wear condition for these composites in our multi-directional pin-on-disc test. So finally, I will summarize the whole thing. Many efforts have been made towards finding a solution of hip and knee joint prosthetic implants going beyond pure UHMWPE. So one thing we should know, that pure UHMWPE is still a very good material, but we need to find some replacement or improvement. PEEK with cross-link polyethylene has shown promise, but needs to be re-evaluated. So it is very important that it is re-evaluated. And PVA Hydrogel and a combination with a Zitarian polymer boundary lubrication provides another promising material, which is non-UHMWPE. And from our research, we have found that epoxy or Su8 or similar thermoset with UHMWPE particles and a boundary lubricant can hold another promise for future evaluation. So this is all about how what has been done in research in biotribology research for non-UHMWPE polymeric systems. So before I end, I would like to introduce you this conference we are organizing called indiatrib.org. So please go to this website and you will find all the information. So if any of you is interested to attend this conference, or if you belong to a company, you may very well try to sponsor our conference. So thank you very much. Okay. Yes, Sam, back to you.
Our sponsor videos. So we have two of these from Optimal, and I'll also release release some handouts from them, and then we will go to Q&A. So, Sujit, if you like to, you can stay on stage. Could you just mute your microphone, please, just so that we can play the videos without any interruption? Thank you very much. Okay.
SRV Tribo Talks. I would like to invite you to take a look at some of the many tribological solutions we and our customers have developed on the SRV test system. For example, the SRV allows you to generate tribo contacts with complex 3-axis movements and measure them in 4 dimensions. The high practical relevance of the simulation and relevant measurement data create valuable knowledge about your product. The ability to use your own prototypes and series parts in the SRV test environment is key to achieving relevant results quickly. To this end, you benefit from an installation space of 50 x 40 x 200 mm. Your components can be tempered up to 300 centigrades. Rolling bodies are found in bearings and gearboxes, often as lubricant systems, but increasingly also dry running. With the SRV, we enable you to screen your greases and coatings under realistic load collectives with relative speeds up to 1 meter per second. Using multi-axial movements and test setups, you can transfer complex movement sequences to model testing in the SRV and thus test the real system on a laboratory scale. The results can be transferred directly into practice or simulation. A very well-known example of such movements is the piston-pin rod-eye contact. Here, the SRV allows you to simultaneously test pin materials, bearing materials and engine oils in one test setup. Tribological model tests provide insights into tribological systems that are otherwise difficult to access. The simulation of internal engine wear processes outside the engine is an impressive example of this. The metallurgical properties of your materials under the influence of temperature can be analyzed in a range from -45 to +1000 centigrade. The simulation scope varies from simple abstracted test geometries to original parts. The test setup shown is used to evaluate high temperature materials and plain bearings. The SRV's ability to represent tribo contacts extremely realistically in a model environment is one of the reasons for this worldwide success. Do not hesitate to call us if you want to address a friction and wear related problem through tribo testing. We will be happy to support you.
Okay, Great stuff. So that was Gregor Patzer from Optimal, recorded there, talking about the SRV platform. So what I'd like to do now is to move on to the Q&A and also to make our attendance certificate live. So that should be down in the bottom left-hand corner for all of you that are interested. Sujit, are you happy to answer questions now? We will run a little over with this event, but we have 5 questions, so I think we can get through these. So we have the first one here from Ben, who asks, in the Liu and Sinha study in Wear, for the CNT-UHMWPE composites, did you also measure elastic modulus as well as hardness? I would expect a bigger change in E than H.
Actually, we did not measure E. So we conducted a macro hardness test, which gives us basically only the hardness. We can relate it to the yield strength of the material, but to measure E, we had to conduct a tensile test, which we could not conduct. So no, we don't have the value of E for those samples.
Sure. We have 2 questions from Nazir here, the first one of which is, sir, you mentioned mixed lubrication. How do you maintain it in pin-on-disc equipment?
Yeah, so basically people have proposed that it is a mixed lubrication, and we have also seen through our various tests, use some of the models. So you will have to go to some of our other papers where we have shown that mixed lubrication can be actually proven if you measure friction and the speed. So there are relation between the friction or the shear stress and the speed, and actually basically under some situation you can get a linear curve. So this proves that mixed lubrication was working, and in fact there is a famous paper by Hugh Spikes from Imperial College. If you are interested, please go to that paper, and also very classical paper by Professor Brian Briscoe, also from Imperial College. So and if you go to our papers as well, you will find that it's possible to actually prove that there is a mixed lubrication. Of course, in a normal pin-on-disc machine, you cannot see the mixed lubrication acting. What you can do is perhaps you can make one side of it as transparent, and then you can do some imaging from the back end, from the back side, and you can show that there is some formation of mixed lubrication. So this is basically theoretically you can prove if you know the shear stress and the velocity, and you conduct the test at different velocity, you can show that there is a mixed lubrication condition here.
Okay, the second question from Nazir, who asks, and how will you confirm it is mixed lubrication conditions? How do you measure the oil film thickness quantitatively?
Yeah, so I have already answered how you confirm the mixed lubrication. But how do you measure the oil film thickness? That is a big problem. And as you know, in mixed lubrication, it is not a uniform film thickness. So that's another big problem. But if you have for example, in hydrodynamic condition where you have got a throughout film formation, then you can use the optical method to measure the film thickness. But in a mixed lubrication, perhaps it is extremely difficult to measure experimentally.
Sure. We have a question here from Dilesh, who asks, what kind of tribological influence can be expected due to the different molecular weight of the polymer, in parentheses, UHMWPE?
So normally what we use is UHMWPE, which I believe has got molecular weight of 3 million or in that range. This is a standard material that we get for UHMWPE. Another polyethylene is high density polyethylene, HDPE, which has also been tested to some extent, but UHMWPE has got better performance. So I don't have any data or even I have not seen any paper where different molecular weight of UHMWPE has been tested. So this is all basically from the same source of UHMWPE that everybody is working on. So, yeah.
A question here from Pedro, who says, "Hello, Professor. Thanks for your talk. How do you evaluate the effects and consequences of absorption of bovine serum, for example, by the polymer, only by hardness measurements?"
So the absorption of bovine serum or even water, if you put them in water, it will absorb a lot of water in it. So up to weight percentage could be up to by 10% depending on the polymer. Okay. But for UHMWPE, it does not absorb so much. So hardness is one way to say how the bulk property has changed. So how do you evaluate the effects? So effects and consequence will be basically you will have to see the tribological effect on the tribology, and so you soak the specimen in that liquid for several hours, sometimes 6 or 10 hours, and then you conduct the tribology test and you see what is the effect. And hardness test, you can get bulk property. So these are things that we can do to find out changes in the bulk property or the tribological property because of soaking.
Okay, great. Just before, we had one final question, a little short one that I'll bring up in a moment. I just wanted to say, for anyone interested in the attendance certificate, please do click on that link now, as that will be getting replaced with another one soon. So come on to our final question, which says, which tribo machine is most appropriate for polymers testing?
So for bio-tribology test, as I was talking about, what is important is the cross shear motion. Cross shear means the wear, the sliding should take place such that the wear tracks meet at an angle. They should not be linear in one direction. So this cross shear can be achieved in multi-directional pin-on-disc machine. So this is there are many researchers, many groups have it. You know, for example, Leeds University, and recently we also have made our own in Kyushu University. So these are different designs that are available, and you can actually make your own, or you can buy them. There are also commercial such machines available. So this is for pin-on-disc machine, multi-directional pin-on-disc machine. But the second stage should be on a simulator. So simulator is a much more advanced machine where it will simulate the hip movement or knee movement, and it will give you crisscross the motion as well as variation in the load, because when we do our daily activity, our loads keep changing. So it will simulate the actual hip operation. So it has to be tested in the simulator before we can think of any in vivo tests. So.
Okay. Great, thank you. So we're going to close the event there, and okay. Apologies for those people who didn't get their questions answered. So let me just bring up our final slides. Our final slide. So I just want to say thank you, Sujit, very much for that fascinating talk. That was fantastic. I enjoyed every minute of it. I just want to say thank you, all of you, for asking great questions as well. We love to, we love to have this interaction with our audience. I just want to say thank you to Optimal Instruments for the support to run this event. We would not be able to do anything that we do here at Surface Ventures without our partners. I'd just like to give a reminder to all to visit our website to look at previous talks. The replay for this talk will be uploaded within the next day. And I'd just like to say our next event will be will be up on the 28th of July. So let me just bring up the registration site for that. This will also be up on our website later. So please stay tuned for our upcoming emails and LinkedIn posts about this event. And finally, I'd just like to remind you all about our fortnightly newsletter, Modern Surface. By signing up to our mailing list, you will receive this. And finally, I'd just like to say to all of you in the audience, thank you for your support as well. And in future, I would just ask that you, if possible, take the time to advertise these webinars to your contacts. It would be great that we continue to grow our audience and reach even more people. So with that, I'd like to say a final thank you to our speaker, Sujit. Thank you very much for your great talk today and for answering the questions, and to all of you in the audience for joining.
Yeah, thank you, Sam, and your whole team. And I also would like to thank the audience for being here and interacting with me. So it was a very great pleasure for me. Thank you.